Hi everyone, happy to be here today to present our work, MadEye, boosting live video analytics accuracy with adaptive camera configurations. This is work done in collaboration with my wonderful colleagues from Princeton and Rice. So today, cameras are becoming more and more ubiquitous in large organizations and urban areas. These cameras monitor regions of interest for a number of crucial video analytics applications, such as security surveillance and traffic monitoring. In a video analytics pipeline, you typically have a camera that's deployed in a region of interest, and you also have a backend compute server. Users and applications register queries with the compute server to answer questions they may have about the scene. For each query consists of a model, a task, and an object. For example, a user may want to use the YOLO v4 object detection model to know how many cars are in the scene. We call a set of queries a workload. Once the queries have been registered with the compute server, the camera then starts streaming frames to the server. The server then executes all the neural networks on these incoming frames and returns the results back to the users. A key goal of these video analytics pipelines is to deliver high accuracy results, all at low latencies. And in recent years, there's been a lot of work in improving video analytics pipelines. For example, there's been work done in frame filtering to reduce the amount of redundant inputs in the video stream, thereby reducing network and compute overheads. There's also been work on making or optimizing no network inference, and also on offloading no networks onto the edge. Further, there's been work done on model serving to improve resource utilization and to help platforms better meet SLOs. However, one thing that we've observed is that camera orientation or positioning, which is a crucial piece of the video analytics pipeline, has gone largely unstudied. From the perspective of the camera operator, given a scene, a workload, and a camera deployment, they must determine how to orient the camera. In other words, how to determine the rotation and how to zoom. As we shall see pretty soon, this actually plays a very big role in video analytics pipelines, because the camera orientation largely governs the content that the camera captures. And this has a very big impact on the queries that run on the resulting video frames. In the next few slides, I'll delve into this a bit deeper and give some examples of what these orientations actually look like. So here we have a scene of interest in a busy city street. And one example camera orientation that we can use here is that we can take the camera and we can pan by 30 degrees. And in doing so, we can capture these two cars on the right. Similarly, we can pan in the opposite direction, tilt downwards, and zoom in by a factor of 2, and capture this black car that's on the left using this orientation. And we observe that generally changing orientations has a very big impact on query performance. We see that this is because changing orientations brings new objects into the field of view, and it also helps models find existing objects that they couldn't identify before. So let's consider this example. Here, when we pan the camera by 30 degrees, we can capture 2 additional cars. We capture this large gray van on the left, and this is because when we rotate the camera, this van enters the field of view. More interestingly, we're also able to capture this white van in the back, despite this white van actually being within the field of view in the first image. Here on the right, we have an example using zoom. And we show that by using zoom, we can increase the number of people being detected from 2 to 4. And this is because the objects become enlarged within the frame. And also zooming reduces a lot of background noise in the image. And overall, we see that adapting camera orientations can yield 21 to 35% higher accuracies over just using the best single orientation for a video. So to reap these accuracy wins in practice, we look towards using pan, tilt, zoom, or PTZ cameras. PTZ cameras offer configurable pan, tilt, and zoom knobs to enable the camera to navigate to different parts of the scene and capture new objects. PTZ cameras have been growing significantly in popularity in recent years, and in 2023, the PTZ camera global market value had exceeded $1.7 billion and is expected to grow steadily in coming years. So using PTZ cameras, our problem now becomes, at each time step, which orientation should the camera move to maximize the accuracy of the workload? So to solve this problem, there were several key challenges we had to overcome. The first challenge is search space exploration. There are many different orientations within the search space due to the large amount of different rotational and zoom configurations. And also, choosing a suboptimal orientation can incur considerable losses in accuracy. We see that in some of our experiments. By just choosing the second best orientation, we can expect to see median dips of 4.8% in accuracy loss compared to using the best orientation. Additionally, we see that the best orientation changes rapidly over time, with many switches occurring in well under a second. This is largely because of the complexities of the queries, as well as the dynamics of the scene. The second challenge that we seek to overcome is diverse workload sensitivities. Different queries are composed of different models, have different tasks, and are looking for different objects. As a result, changing orientations can cause different queries to have very different effects. So let's see an example on the bottom left. Here, by using the SSD object detection model, when we zoom into this image, we're able to identify two additional people. However, when we consider a slightly different query with a faster RCNN model instead of the SSD model, we can see that zooming in actually results in poor performance since we capture one less object. We conduct some larger experiments using workloads that were derived from existing studies. And we see that using the optimal orientations for one workload on another can incur significant drops in accuracy. So in this graph here, we took workload W1, and we evaluated it using the optimal orientations for workloads W3, W4, W8, W10. And as you can see, by using these orientations with W1, we expect to see pretty significant losses in accuracy. And we see that these similar trends hold for the other workloads as well. So going forward, one of the key observations that we make is that the speed at which commodity PTZ cameras can rotate at today far outpaces the rate at which many operators actually need results, with PTZ cameras being able to rotate at several hundred degrees per second. So we can thus leverage these fast camera speeds to explore many different orientations in a short period of time and just send the most optimal orientation to the server for inference. So let's see this visually. Let's first consider a naive predictive approach. This naive approach tries to predict the best orientation at each time step based solely off of historical data. However, because of the issues I mentioned before, this actually results in very poor performance. In contrast, in our approach that we call MadEye, we leverage the fast PTZ camera speeds to explore many different orientations within the scene. So we use the camera to retrieve images from different rotations and different zoom vectors. And we then use on-camera ML techniques to choose the most optimal orientation to send to the server for inference. In other words, the orientation that would yield the highest accuracy. And we repeat this for each time step. So naturally, this approach raises two key questions. The first question is, what set of orientations should the camera visit? And second question is, what orientations should we select to send to the server for inference? So let's first focus on this challenge in determining which or where to move the camera. So we first take the set of orientations from the prior time step, and we assign each orientation a score. These scores are indicative of how well we believe each image will perform in the future with respect to the workload that's running in the backend server. And these scores are computed based off of historical data. Based off these scores, we identify the worst orientation and the best orientation. And we look at the disparity between these two orientations. If the disparity is high, then we opt to remove the poor performing orientation in favor of a new, potentially more fruitful one. To do this, we take advantage of this key observation that the best orientations are typically clustered together. Because of this, we consider all the neighbors of the best orientation. To determine which neighbor to add to the set of orientations, we look at where the objects are located in the best orientation. In this example, because all the objects are clustered towards the right, we select the right neighbor of the best orientation to add to our set, and for the camera to explore in the next time step. So to recap, if the scores between the best and worst orientations if the disparity between the scores of the best and worst orientations is high, we opt to remove the poor performing orientation in favor of this new, potentially more fruitful one. And in addition, we run a reachability and path selection algorithm to determine how feasible the set of orientations is for the camera to visit. And for more details, please see our paper. So the second challenge we aim to tackle is how do we efficiently select which orientations are the most relevant for inference. And we're primarily constrained here by limited on-camera compute resources, which makes it difficult to run many more compute-intensive models. So we first make the observation that query sensitivity is deeply rooted in how query models find and characterize objects, rather than how the queries post-process the results. Thus, we make use of a lightweight on-camera object detection model to capture this behavior. In other words, we want these object detection models to approximate the query model behaviors. To train our approximation models, we take multiple images from different orientations. And we run our workload models on each one of these images and get bounding box predictions. Then using both the images and these bounding box predictions, we give them to our approximation model for training. And we perform training every several minutes to ensure that a model is able to keep up with the dynamics of the scene. During inference, the camera will retrieve images from multiple different orientations. And the approximation model will run on each of these images. The approximation model will identify all the relevant objects in these orientations. Because in this example, we're just concerned with people counting, this approximation model will just identify the people. We then take the count of the people in each of these images and compute what we call query relevance scores for each one. These query relevance scores are indicative of how well we believe each orientation will perform when run on the workload. And because the second image has the highest query relevance score, we send that to the server for inference. So let's put everything together. In MadEye, the camera will sweep through multiple different orientations. Then these orientations will be sent to our on-camera approximation models for inference. The approximation models will then select the most relevant orientation from the set and send that to the server for inference. Once these frames arrive at the server, the compute server executes the query models on them, and the results are given to the users. Then periodically, the compute server will train the approximation models on new images and forward the updated weights back to the camera. For our evaluation, we look at a number of important questions. So how much does MadEye improve workload accuracy? What are the trends when changing network speeds and frame rates? And how does MadEye compare against a multi-arm bandit baseline? We also conduct additional experiments with multiple cameras, individual queries, additional baselines, as well as commodity PTZ camera hardware. And for more details, you can see our paper on those. So we observed that across multiple videos and workloads, MadEye is able to increase median workload accuracies by 2 to 25% compared to an Oracle fixed orientation strategy. This Oracle fixed orientation strategy is essentially the accuracy we would get We took the best single orientation for each video. And this dark green bar, Oracle Dynamic Orientations, captures the accuracy that we would get if we were to use the best orientation at each time step. And MadEye is able to get significant accuracy wins over this Oracle fixed orientation baseline because of our use of the fast PTZ camera speeds to explore many different orientations. We also evaluate at multiple different network speeds and frame rates, and we observe that at higher network speeds and lower frame rates, we're able to reap higher accuracy wins because we're able to get more time to explore more orientations, and we're able to send more images to the server for inference. We also compare MadEye against a multi-GR embedded algorithm baseline due to our search problem framing. And we see whether we're able to reap significant accuracy wins over this baseline, which uses a naive predictive approach solely based off of historical data. Whereas in contrast, MadEye also takes into account the current scene dynamics and scene content. So in conclusion, today I discussed the importance of camera orientations for video analytics workloads. I introduced MadEye, which is a camera server system for automatically tuning PTZ camera orientations in order to maximize overall workload accuracy. And across multiple videos and workloads, MadEye is able to increase accuracy by 2 to 25% over an Oracle fixed camera approach. Thank you all very much for listening, and please do let me know if you have any questions.